So a very good evening once again. So today we are going to be considering differential entropy and Gaussian channel. And so far we've been describing certain concepts in information measure, where we've talked about, where we've actually concentrated on discrete distributions or discrete random variables. Now we want to talk a bit about the continuous random variables. And in our last class, we were able to cover channel capacity, and we made mention of some codes that in order to achieve optimal codes that will achieve rates that are, way below the capacity of the channel, or better still, less than the capacity of the channel with minimum probability of error, that such codes that could be designed from such an engagement could either be block codes or convolution codes. And we made mention that block codes are used to map a block of information or bits into the channel code word, and there's no dependence on past information bits. And also that the convolution codes are codes where each output block depends not only on the current input block, but also on some past inputs. And as such, we're going to be talking about error control codes, where we talk about few block codes, convolution codes. Then we talk about the maximum likelihood decoding scheme. And then we'll walk around a few examples and then see how we could design some, let's say, achievable codes in the communication system, channel codes. Well, that's it for our last lecture. And now, before I begin, I'd love to entertain your views. Do we have any questions so far? Anything bothering you as far as this course is concerned before we move on? So I'd love to hear from you. Feedback, please. Any feedback from you going by what we've been addressing so far in this class? Sure, you want to unmute so we could hear you.
Hello, sir.
Yeah, where were you?
I can hear you now.
Yes. Any questions so far, going by what we've been addressing in this course?
Yes, I think my only, not a question anyway, it's just to remind you of your promise that you give us solved examples so we can use it to rehearse for exams.
Okay. Okay, yeah, that's not going to be a problem. How about Mr. Adeyemo? Any questions so far?
Yeah, none yet. Just like Engineer Ebong said, I think I'm in support of that too. If you could help. Is there going to be maybe something like an area of concentration where we can focus our attention on?
Like I always say,
for the exam, sir.
Okay, like I always say, my goal is not to prepare you for exam. My goal is to prepare you to prepare you as far as the knowledge area is concerned, so you are able to apply this in the field.
It's okay. That's a good one.
Yeah,
it's a good one, sir.
Then for exam, then we should be able to walk through some examples. Then we'll have a written quiz, so to boost our confidence and also check our level of preparedness. But I don't think exam should be anything to worry about right now.
All right, sir. All right.
Yeah. Okay.
Thank you so much.
You're welcome. So then we just hit the ground running for today. So we'll begin with differential entropy. Okay. So now when we talk about differential entropy, like I mentioned earlier, that so far our focus has been on discrete entropy. And now we want to talk about differential entropy, which relates with continuous distribution. Okay, this has to do with continuous distributions. And not discrete, okay? Not discrete distribution. Okay. So hence, the differential entropy is usually referred to as continuous entropy. Okay, so I want to say this is the same as continuous entropy. And as such, we use the lowercase h to describe this entropy. So when we talk in terms of the discrete entropy, we use the capital letter H just to distinguish between them. And for discrete, as you already know, we use the sigma. And then for the continuous, we are going to be using the integral sign, which is the equivalent of the sigma for discrete. And now this time is for continuous. So in some other tests, this may also be denoted as h of f, where f is the density function. And then at this point, we could provide a formal definition. So the differential entropy of a continuous random variable, say x, with density f of x, can be defined as, so here we say we have a continuous random variable x with a distribution f of x. And now the continuous entropy, or better still, the differential entropy, is therefore given as h of x, negative integral, where over a, which is the support set of the random variable, then f of x log f of x dx. Okay?
Can you see me 45?
And in this case, we can equally conclude just more like in the discrete sense that sigma, that's integral f of x, is the same as the expectation value. Okay? So here we want to say this is the expectation value of log f of x, right? So we are just doing the same thing, okay? And we already made mention that A, in this case, is a support set of the random variable. And X, in this case, is not a discrete random variable, but it is a continuous random variable. Okay. Perfect. So it should be noted that care must be taken in applying the properties of discrete entropy to differential entropy, largely because the probability density function, say f of x, could be greater than 1. Okay. And if that is true, as we'll find out shortly, then differential entropy does not share all the properties of discrete entropy. And now love us to look at a brief example or just a few examples. Okay. So let us consider, let's consider a uniform distribution, say f of x, given as 1 over a, when the interval of x is some value between 0 and say alpha, and then it is 0 otherwise. Okay. So going by the definition of the differential entropy, since we have a continuous function of density, then the differential entropy will therefore be the same as integral x taking on value from alpha, from 0 to alpha, then f of x log f of x dx. And this is going to give us negative integral x equal to 0 to alpha 1 over a log 1 over a dx. And once we integrate this, all of these parameters have nothing to do with x, so we can assume it to be a constant. So, and if we do that, well, let's assume this is alpha, so as to be able to put up our parameters, you know, so as to be able to resolve this. Then this, or better still, we could leave it the way it is, and then just differentiate. Yeah. So then this is going to give us negative 1 over a log 1 over a integral dx, x equal to 0 to alpha. And this is going to give us negative 1 over a log 1 over a x, for which x is equal to 0 to alpha. Then this is going to give us 1 over a negative into bracket log 1 over a. That will be x minus 0. That's alpha minus 0, then alpha. Now, should alpha be the same as a, then this will be the same as negative 1 over a log 1 over a times a. So this will truncate this, and this is going to give us negative log 1 over a. And this is going to be the same as negative log a, which is the same as log e. Okay, so it means here the entropy, or better still, the differential entropy is the same as log a. That's simple. Now, what if we have a normal distribution? So let's assume you ask, okay, fine, let us give us the differential entropy for a function that has the normal distribution. That is a normal distribution, meaning it has a mean 0 and a variance sigma squared. Okay, so we already know, so let us recall, recall that normal distribution is given as f of x 1 over sigma square root of 2 pi exponential minus 1 over 2 x minus mu, which is the mean, divided by sigma all squared, right? So now, if that is that, then we already know that f of x is the same as the probability density function. Now, sigma is the standard deviation. Mu is the mean, and sigma squared is the variance. Okay, And soon we'll see how this helps us to estimate the noise variance when we begin to talk about the Gaussian channel. So in this case, it means that the mean is 0 because the normal distribution described as 0 mean. So this means the mean is 0 and our variance is the same as sigma squared. So once we plug that in, then this function, this distribution, will now become 1 over sigma 2 pi epsilon negative half. Then this reduces to 0. That will be x over sigma squared. So we already know that the differential entropy is the same as negative integral f of x log f of x dx. So once we plug this in, then we are going to have negative integral f of x. I would love to leave this way because this is the expectation value. Then log, then let's plug this in. 1 over sigma square root of 2 pi epsilon minus half x over sigma squared dx. Okay. Now, should we take the natural logarithm in this case? Let's consider this to be log to base e. So it means that the unit of measure is going to be in nats and not in base, right? Not going to be in base because it's in base e. We already mentioned that. If it's in base 10, that's Hartley. If it's in base 2, it's in base. So if we should take the natural logarithm, which is the same as lim, then that's log to base e, then we can, this should be in natural logarithm. So once we do this, then what do we have? So I need to clear this board. So we have more space. So this is where we are at. H of x is the same as negative f of x integral log to base e 1 over square root pi epsilon minus half x over sigma squared dx. Okay, so this is a product between this and this. So then this becomes addition by the rules of logarithm. So the integral f of x will be the natural logarithm 1 over sigma square root of 2 pi plus log to base e epsilon minus 1 over 2 s over sigma squared dx, right? So log down, okay? Then from this, we also have integral f of x log to base e 1 over sigma square root of 2 pi. Then once this, because log to base log e base e this time, so by the rule of natural logarithm again, so the power comes down, so this becomes minus 1 over 2 x over sigma squared log e base e, and this is going to reduce to 1, so dx. So from this we have this negative f of x log to base e 1 over sigma square root of 2 pi minus 1 over 2 x over sigma or squared dx. Okay, and now, well, this is another way of writing negative integral f of x minus log to base e sigma root 2 pi. I just remove this 1 minus 1 over 2 s over sigma. Then this one, then negative this is the same as this. Recall how we've been playing with our entropy information, then squared dx. Okay, Now that we have done this, so we could also rewrite this. Let's have something cleaner. F of x negative log to base e square root of 2 pi sigma squared. So the square root of sigma squared gives us sigma. So it's the same way of writing that, and negative. Then we could say this is x squared divided by 2 sigma squared dx. Perfect. Okay. So from here, we already know if we take the expectation value of this is a constant. Recall, this is the expectation value. Okay. Now, this sigma f of x is equivalent to our sigma p of x, which is equivalent to our expectation value. Okay, this is what we've been playing with. So if that is true, then we could rewrite our entropy to be the same as negative times negative, that's positive, log to base e, because this is a constant, sigma squared, plus the expectation value, x squared divided by 2 sigma squared. Okay. Now, well, in dealing with this is the energy, right? X squared. This is more like the power and the noise energy. Okay. Fine. And this also can be written as log to base e into bracket 2 pi sigma squared 1 over 2, which is the same as the square root, plus the expectation value x squared over 2 sigma squared. And now this is the same as half log to base e 2 pi sigma squared plus, now should the signal energy be equivalent to the power, to the noise energy, this is going to reduce to 1 over 2, right? And then if we have that, then the next thing here is 1 over 2 log to base e 2 pi sigma squared. And this is going to be the same thing as log e base e, because log e base e is the same as 1. So we can compress this into a single value, so 1 over 2 log, this addition becomes a product, then log to base e 2 pi e sigma squared. Okay, so this becomes the differential entropy in that. And once we perform change of base by change of base, we should be able to have something similar in bits. That's h of x will be the same as 1 over 2 log to base e 2 pi e sigma squared bits. Okay, so we're just trying to play with a few things to just look figured out 2 different distributions. Okay, yeah, the uniform distribution and the normal distribution. Well, we are going to come back to this shortly. Okay, so just take note of this. This is going to be very, very useful as we progress in this study. Okay, now the differential entropy of a uniformly distributed random variable. Okay, this is what it is. Okay, we just showed it here. So we'll begin to evoke this as we progress. Now, let us consider a few details about the differential entropy, because it's more like what we've been talking about, only that this time we are not talking in discrete terms, we're talking in continuous terms. So everything you already know, most of what you already know subsists, okay? So let us consider the joint differential entropy. So let's try to, let's say h of x1, S2 all the way to Sn is the joint differential entropy of a set, S1, S2 all the way to Sn, having, let's assume this has the density function, f of S1, S2 all the way to Sn, okay? then the differential entropy will be the same. That's of this joint distribution, be the same as negative f of Sn log f of Sn dxn. So when x and y, for instance, have a joint density function, okay, then we could define the conditional entropy. So the conditional entropy will be the same as the conditional entropy of x given y will be the same as negative integral the joint distribution log the conditional distribution dx dy. And we already know from Bayes' theorem that the conditional distribution is the same as the ratio of the joint distribution divided by the distribution of y. And then by chain rule, we also have the same as we already know, which is given as the joint entropy minus the output entropy. And then the relative entropy also follows directly, which is the callback-Leibler distance between two distributions or two densities, CF and G, is the same as the integral F log F over G dF dg, okay? And you should note that the relative entropy is finite only if the support set of F is contained in the support set of G, okay? So if the support set of F is not contained in G, then this will be infinite. And also the mutual information follows directly from this, which is the integral, the joint distribution, y, plus y, f of x, f of y, dx dy. And then by chain rule, we already know that the mutual information is given as the difference between the source entropy and the conditional entropy, whereas the equivocation. And then it's also the same as the difference between the output entropy and the conditional entropy. Then is the same as the sum of the source entropy and the destination or output entropy minus the joint entropy xy. And then this is also the same as the relative entropy between the joint distribution and the product distributions. F of y. Okay, now that we've sorted this, so let us look at a few properties. A few properties of differential entropy. So we have that the relative entropy between two densities must be non-negative, with equality if and only if the two densities are equal almost everywhere. So with equality if and only if both densities are equal almost everywhere. And then the mutual information is also non-negative. Then we also know that the equivocation is less or equal to the source entropy, like we already have. And with equality, if and only if x and y are independent. Then the chain rule for differential entropy is as in the case of the discrete entropy, where we have the chain rule, differential entropy is given by h of x1 all the way to Sn is the same as the sum I is equal to 1 to n h of the conditional entropy 1 all the way to Si minus 1, which is less than or equal to the sum of all the entropies for which I take some values from 1 to n. Okay. And then this we will show the fifth property here, that the differential entropy is translational invariant. Let's see if that's where. So if C is constant, so we have h of x plus C, for which C is constant, is the same as h of x. So the constant parameter have no impact on the entropy. And then the differential entropy, it's not invariant under arbitrary invertible map. So what do we mean? So if we have a constant, say, acting as a scaling parameter, then we'll have to add the determinant of that, the log of the determinant of that parameter to the entropy. Note that this is added, but this is a scaling parameter, okay? So the idea is that for a vector valued random variable x, and an invertible square matrix, invertible square matrix, say A, then h of ax will be the same as h of x plus log of the determinant of A. Okay, so we'll prove this, all of these things. Then another interesting property is that for the transformation from a random vector to another random vector, with same dimension, say y is the same as mx, the corresponding entropies are related by the Jacobian, right? So that h of y is less than or equal to h of x plus the integral, that I say the expectation or the expected value log the Jacobian, the m, the x, then the x. Now, mod the m, the x is the Jacobian of the transformation, okay? M. So here you observe that we have the inequality. So that inequality becomes equality if the transform is a bijection. And when M is a rigid rotation, translation, or combination thereof, then the Jacobian determinant is always unity. And then H of Y will be the same as H of X, okay? And then one more property that we'll consider is that if a random vector, for instance, a random vector X is an element in this real distribution, then, and it has a mean of 0, and then a covariance matrix, say K, then the differential entropy of X is less than or equal to half log then of the determinant. Recall, we already showed 2 pi ek, okay? We already showed this earlier for a normal distribution, having a 0 mean and a variance or covariance k. The last time we used sigma, right? So this is going to be the same as half log 2 pi e to the power of n determinant k. Okay. Now equality will exist here with equality. That's it, with equality. If and only if S is jointly Gaussian. Okay. And we already know that covariance measures the direction of the relationship between two variables. Okay. So, well, now we're going to apply some of these things in Gaussian channel. So I would love us to look up, let's move straight into the Gaussian channel, and then we'll see how this applies to something close to a practical channel. Okay. Okay, so in your communication system, you must have heard of a Gaussian channel, a Rayleigh channel, a Rician channel, and all of that. So in the practical sense, when we have a direct line of sight between your transceivers, then we actually deal with a Gaussian channel. And most of the time, this is what we have in cable when we use cable as the medium of communication for your channel, your wired communication, even your direct microwave link point to point. So we deal with Gaussian. But when we have the line of sight and a multipath, we talk about Rayleigh. And if we don't have a direct line of sight at all, everything is all multipath, then we say Rician, okay? But this time we want to consider the simplest model, which helps provide an approximation for other models, which is the Gaussian channel. So, so in your antennas and propagation course, you're going to go into all of those things in detail. Okay. So now that we already explained that the Gaussian channel is a model for a communication channel with a dominant line of sight between the transmitter and the receiver. Examples could be your telephone systems, your satellite links, even in your base station, your mobile communication, where you have those drums, you know, some of your work in telecom companies. So you have your band antennas, your sectorized antennas, for instance. Those ones are for coverage. Then you have these microwave links, okay? So this provides direct line of sight, okay? So at times you have some BTS where you have so many of these drums, right? so many of these drums, you know, and we say this is the BSC, okay, while this is the BTS, okay? So with this, we are able to communicate with other base stations, okay? Where you just have all of those single microwave whatsoever, okay? Direct line of sight. So here, what we're actually going to be dealing with is a pure Gaussian channel, okay? And how do we model this? We say, well, if we have, say, a symbol which is transmitted, and we have a channel. This channel is more like an additive channel. So it means that here, with the noise component, say Zi, then what is going to be the output Y sub I? So the output this time is going to be the sum of the input signal plus the noise signal, okay? So this is just, and then in this case, the noise will have a Gaussian distribution, which is a normal distribution, zero mean and n variance, which tells us the noise. So the variance this time, recall that the variance has to do with two different things. So the variance this time is going to check the difference between Y and X given Z, okay? So this, so for us to be able to estimate the difference, so the difference between this and this is going to give us the noise parameter, okay? Okay, because Y sub I minus X sub I is going to give us Z sub I, okay? So that is why in this case, the variance here is to estimate the level of distortion in this communication channels model, okay? Okay, so if this is clear, then the capacity of this channel may be infinite if the noise variance is zero, okay? And then the receiver receives the transmitted symbol perfectly, okay? So if the noise variance here, N, is zero, so let's say this reduces to zero, so it means that the receiver is going to receive the signal without any error. So since X can take on any real value, then the channel can transmit an arbitrary real number with no error. That's the idea, okay? So whatsoever we want to do is to find a way to limit this contribution, the noise contribution in this Gaussian channel. Okay, now, if we got that, so let us move on. So, okay, before I move on, what is, if we want to estimate the power, the average power of a signal, what is it? Or the energy of a signal, what is it? This is more like from your signal, your signals and systems, because I just want to begin to quote now. I just want to move on and just quote a certain things, okay? So we want to talk about the energy and the power constraint, because the most common limitation on the input is the energy or the power constraint, okay? So here, the issue we're going to be, okay, let's wipe this. This is a little messy. Okay. So we already mentioned that we have the input, S sub I. It goes into the channel. Then we have the noise, Z sub I, and then we expect an output, Y sub I. And the model in this case is that Y sub I is the same as the input signal plus the noise contribution, for which Z has a normal distribution with zero mean and N variance, right? Noise variance. So, and you'll observe that the major constraint we are going to be having on this input is going to be the power of this signal relative to the power of the noise, okay? So the energy or power constraint is the major limitation in the communication system. So hence, we have to assume an average power constraint, okay? And for any code word, say S1, S2, all the way to Sn transmitted over the channel, we are going to require 1 over n, the average of it, 1 over n, that's we have n symbols, 1 over n is going to give us the average of the total sum of the power. So that's x sub I squared, which should be less than or equal to p, okay? Now, why is our power s sub I squared? I need someone to help me out now. We have quite a number of guys in class. So why is this power s sub I squared? Do you know? The energy of the signal, why is it s sub I squared? Hello?
I assume that it's just to strengthen the signal because of the losses.
Why is it not x sub I cubed? Why is the energy of the signal not s sub I cubed? Why is it not s sub I to the power 5 or s sub I to the power 4? Why is it cube squared? That's all I just want to know. Is it an assumption?
No idea, sir.
Okay, so I think I'll have to review that because I wanted to jump up and just move on. Okay, let's now. Yeah, you just said no idea. What I want to get the views of some other guys in class before I move on. For others, are you on the same page or you have something in mind? Because it's going to take me off this, just review something else, then come back to this. It's not part of what we're supposed to be talking about. So, okay, I can see Mr. Ogaga is in class. Can we hear from you, please?
Yeah, I'm in class, but I'm in a bit of a rowdy environment. That's why I need to.
Okay, so do you know why it is x squared? Why is power or energy of the signal x squared? Any idea?
No, sir. No.
Okay, that's fine. We're going to resolve that. Now we'll just go back to some basic, it's more like the basics, okay? Okay, fine. I just got to open you. So let's quickly recap the energy of a signal, okay? And then we'll come back to what we have to do, okay? So well, let's take it as simple or as basic as it is. I want to believe you remember your circuit, say your resistive circuit, for instance, okay? Where we have a voltage applied across this terminal. Let's assume that is our signal. Then the current flows, I sub t, and then we say this is a resistor. Okay, so we already know that voltage is a separation of charge. Okay, and once we're able to do that, there is a pressure on this system to excite the electrons from wherever they are, and then they begin to move. And then we say once the charges are now mobilized, we say that is current. So we know voltage is a separation of charge. And then current is the same as charge in motion, right? So once we have this, by Ohm's law, we know that the power of this signal or whatsoever is going on here is what? VI, the voltage times current. And we also know by Ohm's law that V is the same as IR, okay? So once we plug that in, so we see that power is the same as IR times I, which is I squared R, okay? And from this, we also know that I is the same as V over R, right? So if we plug that in, then it means that P is the same as V over R squared R, which is V squared over R squared R. Then this truncates this, so the power is V squared over R. Okay? And now, if we assume that R is normalized such that R is the same as 1, then P is the same as V squared. So that's why the power of the signal is always the square of the value Okay, it's not an assumption. Is that clear, please? Is that clear?
Thank you, sir. It's
Okay.
clear.
Okay, now if that is clear, so we are not making some funny assumptions here. And now we know that energy is the work done, right? So if it's the work done over total time, then power is the same as work done over total time. And should energy be the same as the work done, then that's power times time. And then it means that the energy will be the same as the integral taken on these limits, P of t dt, right? And then since we already know that our power, P of t, is the same as V squared t, then the energy will now be integral negative infinity to infinity P of t dt, which is integral negative infinity to infinity V squared of t dt, all right? And then the average power, and then average power, we now have to take on the limit for t when it tends to infinity, then 1 over t, the time period, negative t over 2, t over 2, p of t dt. Okay? So, well, what am I doing here? This is more like your signals and systems, right? Okay, so those are the basics. You must have done those in your elementary studies. So technically, if our signal is now represented as x, then the energy is the same as the integral negative infinity to infinity mod x of t squared dt, okay? So this applies to both periodic and non-periodic signals, periodic and non-periodic signals, okay? So that's what it is. So we have taken the modulus of the signal, okay? So because energy cannot be negative, right? It can be negative. We can only have positive values of energy. Is that okay? And from this expression, so we can also say that for a periodic signal, for instance, that the power is the same as 1 over t naught integral over the fundamental time period mod s of t squared dt. Okay? Okay, and for this for periodic signals, and for non-periodic signals, so we can take the limit as the time period takes some values extending to infinity, negative t over 2, mod s of t squared dt. Okay? Okay, so that's just some basic idea, okay? So if that is clear, so we don't want to make any assumptions, then let us come back to where we stopped. So we already said that we have some code words, x1, s2, all the way to sn, transmitted over the channel, and as such will require 1 over n sigma I equal to 1 to n s of I squared. We know that is the energy, okay? Now, the additive noise is in such a channel may be due to a variety of causes, okay? But you'll recall that by the central limit theorem, the cumulative effect of a large number of distribution of, let's say, some small random effects will give us a distribution that is normal, okay? So if we have a large sample space, we have so many, probably we're considering quite a large number of random variables. So the larger, the better for us. So if it's way beyond 64, something thereabout, then whatsoever we're going to be having for that distribution is going to be approximately a normal distribution. That's what the central, probably want to look that up. That's what the central limit theorem actually states, okay? So the Gaussian assumption is valid for large number of samples, okay? Now, if that is true Then the information capacity of the Gaussian channel with a power constraint P, okay, will now be defined as the maximization of the mutual information such that the function is the same as the expectation value or expected value of x squared, which is the power of the energy, which is going to be less than the power constraint. But the mutual information is also given by the chain rule to be the same as the differential entropy minus h of y given x. It's also the same as h of y minus h of x plus z given y, which is the same as h of y minus h of z given x. Then this is going to give us h of y minus h of z. Okay. Now, you recall from what we already resolved earlier for a normal distribution that the entropy h of z will be the same as 1/2 log 2 pi epsilon the variance n, because in this case we already mentioned that we have a noise variance n. Okay, so if we have this, then this follows directly from the entropy of a multivariate normal distribution. Okay, then we can now look up the entropy of a multivariate normal distribution, for instance. So let's say entropy of the multivariate normal distribution. So if, for instance, we have x1, s2 all the way to Sn. So let's assume these variables or random variables have a multivariate normal distribution. They have a multivariate normal distribution. With mean, mu, and covariance matrix K, then the joint differential entropy S2 all the way to Sn will be the same as the entropy of the normal distribution, for which we have mu, mean mu, and K covariance. And we already know that this will give us half log 2 pi T to the power of n, because it's multivariate, it's not single, there's so many of it, mod K, the variance, okay, bits, because this has K covariance, okay? So the probability density function of x1, s2 all the way to Sn will be given as f of x, which is equal to 1 over square root of 2 pi to the power of n. Because it's not single, it is multivariate, then mod k to the power of half, epsilon minus half. We already showed this earlier. Then x minus mu transpose, then k inverse x minus mu. Okay. So then h of f will now be negative the expectation value, negative 1/2 s minus mu transpose k inverse s minus mu minus natural logarithm. This is the same as log to base e, right? You recall that it's the same as the natural logarithm. square root of 2 pi, the power of n, then mod k dx. So this is now going to give us half, then the expectation value, sigma, I have ij, s of I minus the mu, k inverse, ij, then x of j minus mu sub j plus half the natural logarithm 2 pi n. Okay. Okay. And then this is going to give us half of the expectation value, sigma ij sub I minus mu sub I, s sub j minus mu sub j, k inverse ij plus 1/2 natural logarithm 2 pi and k. Okay. So now I want to write this. I don't want to. So I'll just take it off from here. So this is going to give us already resolved this, then this is now going to give us h of f will give us half sigma ij, the expectation value, s of I minus mu j. Let's put this in bracket. Then s of no, this is j minus j, then s of I minus mu I. That's what we have here. Then k inverse ij plus half natural logarithm 2 pi n mod k. Okay, so this is going to give us half sigma I, sigma j, k ij, k inverse ij plus 1/2 natural logarithm 2 pi and mod k. So this is going to give us 1/2 sigma k inverse j sub j plus half natural logarithm 2 pi and mod k. So this is going to give us half sigma j. It's going to give us an identity matrix jj plus half natural logarithm 2 pi and mod k. Okay. And then we now have n/2 plus 1/2 natural logarithm 2 pi and mod k, which is the same as 1/2 natural logarithm 2 pi e and mod k knots. And just the same way we resolve the last, so natural logarithm 2 pi e and mod k bits. So it's the same thing. But the difference now is that this is multivariate, so we have n number of samples to deal with. So with this, then we now come back to where we dropped off, because this is more like a little distraction. So we made mention of h of z is the same as half log 2 pi, because it has a normal distribution. So it means that having a normal distribution, then the differential entropy is the same as this. But so from this, we can now say, because recall that for the Gaussian channel, that y is the same as the transmitted signal plus the noise, right? So if we now take the energy, because we made mention that the major constraint we have is the power and the energy. Okay, so in as much as there is, if there will be loss of signal, then it means that the noise power is beyond the signal power. Okay, so at some point we want to minimize the noise power so as to receive our signal. Okay, so we already know why we have y squared as the energy of the signal. So if we take the expectation value, then we can also take the expectation value of this x plus z all squared. Okay, and now once we resolve this, x plus that is x plus z times x plus z, that'll be x squared plus sz plus sz plus z squared. So that's x squared plus 2xz plus z squared, right? So it means that this is going to give us the expectation value of x squared plus 2 expectation of x, expectation of z, plus the expectation of z squared. Okay. Now, should we reduce the power, the noise level, such that, because this is the same as P plus N, the signal power plus the noise power. That's the implication of what we have here. So in terms of considering the power of the signal, so P is the power signal, then N is the noise signal, and we know the noise variance. So so long we're talking in terms of power, so we're going to have a square of that value. So if Z is, if the expected value of Z is the same as 0, then it means that we're going to knock all of these off, okay? And then, since S and Y are independent and the expectation value is the same as 0, then the entropy of Y is bounded by 1/2 log 2 pi e P plus N, okay? So by applying this result to the bounded mutual information, so what do we get? So we have the bounded mutual information, y, which is h of y minus h of z, right? So let's write this so that things become a little clearer. So we want to talk about the bounded mutual information minus h of z. Just the way we showed before earlier. So this will be less or equal to half log 2 pi e then P plus N minus the noise power log 2 pi E N, right? So this will be less or equal to half log this divided by this. That will be 2 pi E P plus N divided by 2 pi E N, right? And this will be less or equal to half log P plus, this will truncate this, plus N divided by N. And this will be the same as half log 1 plus P over N, right? So in other words, the information capacity of the Gaussian channel becomes the maximization of this, because recall that C is the maximum value of the mutual information when the expected value of this is less than the power constraint. And so the maximum value would be when we have equality. So this would be half log 1 plus P over N. Now you should be used to something like this, okay? And you should know that the maximum is attained when we have the normal distribution of 0 and P variance, okay? Now, this is the capacity of a Gaussian channel with power constraint P and noise variance, okay? So here we have the capacity of a Gaussian channel with power constraint P and noise variance N, okay? Okay, now, since practically realizable channels are band limited, okay, we cannot say where the channel is, that the channel bandwidth is infinite. So it's finite, okay? So if the channel bandwidth is finite, then it means it is band limited. So that is, the transmission channel is defined within a finite bandwidth. So the output of such a channel may be described as the convolution, okay? So if some of these concepts are, if you have some time, you may want to review the lecture note on signals and systems, okay? So some of these things will become clearer. So here we have the signal S of t fed into this channel. Then we also have the noise Z of t. And then we have the channel metric, which is the impulse response of the channel H of t. And then we have Y of t. So here, Y of t will now be the same as S of t plus Z of t. That is what is going into, getting to the receiver, convolving with H of t. So in other words, S of t is the signal waveform, and the Z of t, let's just define. So S of t is the signal waveform. Then Z of t is the waveform of the white Gaussian noise. And then H of t is the impulse response. Impulse response of an ideal bandpass filter which cuts out all frequencies greater than W, okay? And recall the Nyquist Theorem, that it states that a periodic signal must be sampled at more than twice the highest frequency component of the signal to guarantee perfect reconstruction, okay? So as to avoid aliasing, okay? So for us to be able to receive this signal, perfectly, then the sampling frequency should be greater than or equal to twice the maximum frequency, okay? And we know that here, the impulse response, this is the impulse response of an ideal bandpass filter, which cuts out all frequencies greater than this parameter, okay? So it means that here, the sampling rate, T sub S, will be the same as the inverse of the sampling frequency, which will be the same as 1 over 2W, okay? So so sampling a band-limited signal at a sampling rate 1 over 2W, or 1/2 of this bandwidth, is sufficient to reconstruct the signal from the samples. That is, the signal cannot change very much in time interval less than the sampling rate. So if we assume that the channel has a bandwidth of W, we can represent both the input and the output of the samples taken at the sampling rate, okay? And then if we have that the noise power, the noise, let's say the noise in this case Z, has a power spectral density of N naught over 2, that is watts per hertz. Watts per hertz. And then we have a bandwidth of W already. So the noise has a power. So the noise has a power N over 2 times 2W. Okay? Twice the bandwidth, which is the same as N naught W watts per hertz. That's the noise power. Given the bandwidth, we are given the bandwidth W. Okay? So each of the 2WT noise samples this time, noise samples in time T has variance N naught WT divided by 2WT, which is equal to N naught over 2. Okay, that's how we got this, the noise variance. Okay, so that's the implication. So if we look at the input as a vector, okay, in the 2TW dimensional space, for instance. So we see that the received signal is spherically normally distributed about this point with a covariance N naught over 2I. So if the channel is used over the time interval between 0 and the time period T, then what will be the energy of the signal? So the energy per sample. Now the energy per sample will be given as PT divided by 2WT, which is the same as P over 2W. Okay? And now the noise variance per sample will be given as N naught over 2W T over 2WT, which is the same as N naught over 2. So now recall that the channel capacity of the Gaussian channel, as we already showed, is the same as half log 1 plus P over N, right? So if we plug in the energy per sample and the noise variance, so what do we get? That will be half log bracket 1 plus P over 2W divided by N naught over 2, which is the same as half log bracket 1 plus. So this, we truncate this P over N naught W. This is bits per sample. Okay? Now, since there are we have twice the bandwidth samples each second, we have 2W samples per second, then the capacity can be rewritten as C equal to 2W times 1 over 2 log 1 plus P over N naught W. Okay? And this is now going to give us the bandwidth log 1 plus P over the noise bandwidth, bits per second. So this is the capacity of the band-limited Gaussian channel, okay? Capacity of the band-limited limited Gaussian channel with noise spectral density N0 over 2 watts per hertz and power P watts. Okay. Now, from this, we can now conclude that we have C equal to log 1 plus P over N0 W bits per sample. Okay, so when the bandwidth is infinitely large, then the capacity will reduce to P over N0 log P base 2. And then the capacity of a channel with infinite bandwidth is therefore given as this. This is the capacity of a channel with infinite bandwidth. So you observe that the capacity grows linearly with power. You see, the capacity is directly proportional to the power. So as you increase the power of the signal, then the capacity of the channel equally increases. Okay, so I think this is a good place to stop. We have a few topics to still cover. So I want to confirm first if we have any question, so we don't overstretch the class. Okay, any question, please? Any question?
No question, sir, from my end.